For a long time, GPUs felt like the perfect answer for artificial intelligence. They were fast, parallel, and already widely available. When early AI models needed massive amounts of computation, GPUs stepped in and carried the load. That success made one thing feel obvious. If AI keeps growing, we just need more GPUs. But as AI has matured, cracks have started to appear, not because GPUs are weak, but because they were never designed for what modern AI has become. To understand why GPUs are starting to struggle, we need to look at what they were built for in the first place. GPUs were created for graphics. Their job was to draw millions of pixels at once, handle textures, lighting, and visual effects. That kind of work is highly parallel, which made GPUs a good fit for early machine learning. Training neural networks also involves repeating similar calculations many times, so the match seemed natural. For years, that worked well enough. But modern AI is no longer just about raw calculation. It is about scale, memory, and communication. Large models today are not small programs running on one chip. They are massive systems spread across hundreds or thousands of processors. These processors constantly exchange data. Every layer of a model needs information from the previous one. Every update requires synchronization. Every inefficiency gets amplified as models grow. This is where GPUs begin to struggle. A single GPU is powerful, but modern AI rarely runs on one GPU. It runs on clusters, and clusters introduce overhead. Data has to move between chips. That movement takes time and energy. Even with fast interconnects, communication becomes a bottleneck. As models scale up, the cost of moving data starts to rival the cost of computation itself. Power consumption is another issue. Large GPU clusters draw enormous amounts of electricity. Cooling those systems is expensive and complex. Data centers are already hitting limits in power availability and thermal capacity. Adding more GPUs does not scale cleanly. It scales infrastructure problems. There is also the issue of efficiency. When you add more GPUs, performance does not increase in a straight line. Each additional chip brings diminishing returns. Synchronization delays grow. Idle time increases. The system becomes harder to optimize. Engineers spend more time managing the hardware than improving the model. This is not a failure of GPUs. It is a mismatch between design and demand. GPUs were not designed to be stitched together into massive, tightly synchronized AI factories. They were adapted for that role because they were the best option available at the time. Now, the limits of that adaptation are becoming clear. Another challenge is memory. Modern AI models are hungry for memory. Not just capacity, but bandwidth. GPUs rely on external memory systems, and accessing that memory efficiently across clusters is difficult. When models exceed local memory limits, performance drops sharply. Engineers resort to complex techniques just to make things fit. All of this adds friction. As a result, companies are starting to ask a different question. Instead of asking how to scale GPUs further, they are asking whether GPUs should remain the default at all. This is where alternative approaches come into focus. Some companies are building specialized accelerators designed only for AI workloads. These chips remove features that are unnecessary for machine learning and focus entirely on data flow, memory access, and model structure. Others are experimenting with new architectures that reduce the need for constant communication between chips. Instead of spreading models across many processors, they aim to keep as much work as possible in one place. This is not about replacing GPUs overnight. GPUs are still incredibly useful. They are flexible, well-supported, and deeply integrated into existing systems. For many workloads, they remain the most practical choice. What comes next is likely not a single solution. Instead of one dominant chip, the future may involve multiple types of hardware, each optimized for different stages of AI work. GPUs may continue to handle inference and mixed workloads. Specialized chips may take over large-scale training. Custom systems may appear in research and government labs. The idea that more progress always means more GPUs is starting to fade. This shift is subtle but important. It changes how data centers are designed. It changes how models are built. It changes how engineers think about performance. Instead of stacking hardware endlessly, the focus moves toward efficiency, balance, and architecture. GPUs will not disappear. They have earned their place, but they are no longer the only answer. The real story is not that GPUs are failing. It is that AI has outgrown the assumptions that made GPUs the obvious choice. As models become larger, more complex, and more interconnected, hardware needs to evolve with them. That evolution will not happen overnight. It will happen quietly through experimentation, specialization, and gradual adoption. And years from now, when AI systems look very different from today's clusters, it will be clear that this moment marked a turning point.